Okay, C10, Euler number E, and exponential function. In physics, there are two E's, the mathematical E, that is also called the Euler number, and we also have the same symbol, it's electric charge. Of the magnitude of the electric charge of the electron is a very tiny number that we also use E for that one, but we can distinguish in any case. E is a very special number whose exponential is a number, and it's the powers of x, the exponential function. Its derivative, it's itself. It came from the computation of interest rate. So who computed this is a simplest definition of this E, and it appears in various problems because of this fundamental nature of it's a derivative itself. Let's see. So we will reproduce this number. It is irrational number. And remember, it is very simple. 1 plus something. Something is very tiny, and its power is very large. So they are mutually reciprocal. Okay, we recall the binomial expansion. So I believe everybody knows this very well. Okay, why don't we substitute 1 here and 1 over n and follow this expansion formula. Okay, if I substitute 1 here and 1 over n here, we have n factorial in the numerator, k factorial in the denominator. The n-dependent part is this. And this is trivial. This is 1. So we don't have to worry about this. And let me say this n factorial is the product of n numbers from 1 to so on. This is a product of from 1 to somewhere around here, n minus k, because k is a positive number. So we have exact cancellation between these two. So what is the smallest number in the product? That is n minus k plus 1. So we have n minus k plus 1 here after this cancellation. So we still have k factorial in the denominator. And let's see, it's a n minus 0 all the way through n minus k minus 1. So from 0 to k minus 1 is equivalent to from 1 to k. So there are k factors. The counting number is trivial. However, we can always make mistake. So slow down and check it carefully. We have n factors. However, we have the denominator that is k to the power of n. So I can distribute this power one by one and here and simplify the expression. So that is n divided by n. That's 1. This is 1 minus 1 over n, and then it's a 2 minus 1 over n, and so on. The 1 minus 2, 1/nth, 2/nth. Therefore, at the end of the day, the last term, the last factor is simplified as 1 minus k minus 1 over n. Still, we have k factorial in the denominator. By the way, for a finite k, for a finite k, everything in the second term, they disappear as n goes to infinity. Sure, if we have a very large value of k that approaches the upper limit, that is not expressed in this manner. However, we can never approach that point because n is going ahead to infinity in advance. So I can make a very simple expression. Simplification is allowed to find that because this one is everything is one and I have only a single factor in each term, that is 1 over k factorial. By the way, here we have a k factorial that is a 0 factorial. 0 factorial does not equal to 0. 0 factorial means I didn't multiply anything. That means it is a 1. So 1 over 0 factorial is 1. What is this? 1. What is 1 half? 1/6, and so on. We recall the method how to improve the computation of an approximate number. So I just try to compute the 10 digits. So you don't have to follow, but perhaps a few of you might have tried. So raise your hand or tell me if you have reproduced my result for square root of 2. Is there anyone? Is there anyone? Unfortunately not. I could have given you a bonus point. Sorry about that. Okay. So that is not our main issue. Let me pass. But always you can, in principle, compute this kind of number in an algebraic way. Only if we have developed the algebraic way to compute something, we can ask the computer, whatever ChatGPT can compute, but ask some computer program to compute accurate number as possible. So at least you don't compute by hand, you must be able to control the error, whether you order the computer to do that or not. So next one, explain the laws of exponents. And the laws of exponents are very simple. We learned from middle school. So I think I don't have to repeat, but this power, base, and this power, or exponent. So repeated multiplication, we have repeated addition by n times, we say it is n times a. So repeated multiplication of a by n times, we say n to the n. Okay, so if we have a product, then we have a law of exponent. So number of factors, there are m factors, then the result is m plus n. So trivial. And we know the reciprocal. So a to the nth multiplied by something is 1. So this is a multiplicative identity. I'm looking for multiplicative, the inverse. Multiplicative inverse is nothing but this, and this is identical to a to the minus n. Everybody knows And another power law, that is, so you have two powers consecutively, then it becomes the product. The exponent becomes a product. So what's that? Typo. We don't need this. You could have found this. And in a similar manner, mixture. So there are three kinds of notation for this. Uh, I assume it is A is a positive. If it's not the case, it looks complicated. So here we define nth root. Nth root, if I write nth root, that usually means it's a positive case. But these kind of one can be proved in a very simple way if I make use of the Bernoulli's definition of the Euler number. The reason is that you will find why it is convenient. For example, among various A, there is a special number that is E. A of x, A to the x, and E to the x, they have a very similar nature. After rescaling it, they become equivalent, but so it is a much more, it is easier to compute. So we first consider exponential function, but the reason is that in physics problem, it is this one appears dominantly. Okay, so why don't we make use of Bernoulli definition? We have this one and this one in the limit as n goes to infinity. In fact, in general, it should have been written in this form: 1 plus 1 over n to the n, and we have a different, they are dummy, so I should have written in this manner. However, in that case, I can assume that n prime is greater than n, then I can replace this one with the n plus delta, something like that, and n plus delta 1 plus in this manner. So in that case, I can combine the same power with the same power, and in addition, there is some finite difference, that is a delta, and we have n plus a delta. However, because this is a finite, as n goes to n is the other, this one, as n goes to infinity, this guy vanishes. So I can always ignore the different powers. So if I have the same powers, then I can simply combine them, expand. If I expand, then it is 1, and it is easy to find that 1 over n has x plus y, and this product is xy divided by n squared. The very, very good nature of the Bernoulli definition is that if I apply the binomial expansion, unfortunately, no, fortunately, this the dirty term vanishes absolutely. Absolutely. You can make use of this expression, and why don't you substitute, for example, plus 1 over n squared, arbitrary finite number, or higher. Any other higher order power, they may appear, but at the end of the day, they disappear. They die completely. As a result, so this term vanishes. Oh, it is very, very similar to the original definition of the exponential. This is what I have done is just replace this x with x plus y. So immediately I can prove the law of exponent in this case, especially in the case of the exponential function. The Euler number is a very, very convenient. Explain how to compute 1 over e, okay, numerically from the definition. Okay, 1 over e. So we learned that this is fine. And yes, this one comes from the original definition of the Bernoulli definition. Okay, that's fine. And then we can make use of the geometric series. You are familiar with this as far as the absolute value of x is less than 1. So why don't you expand this power series expansion? It's an oscillating series, but we have a power increasing 1 by 1, and there is nothing but the single power. Okay, 1 over n, 1 over n squared, blah, blah, blah. However, we know very well that this guy or higher order always disappear. So I don't need that. I don't want it. And you, sorry about that, disappear forever. Finally, I can express this one as a very simple form. Wait a second. Why don't we define this one in this manner? I have pulled this 1 over n in here and remaining pieces. And the 1 over n is factored out, and in these simplified is 1 minus 1 over n. I can find this is a geometric series. I can sum this geometric series because this is a tiny number, at least 1 over n is less than 1 as n goes to infinity. So I can sum them all, the geometric series. This is sum. And we take the limit as n goes to infinity. That's what I'm doing. And finally, at the end of the day, the tedious calculation, but final result is a trivial. The final result says we have a factor of minus 1 with a power in addition to 1 over k factorial. So that's the reason we have a exponential function. If I substitute minus x, it's also working. And if I substitute x, then, for example, this is E, and I attach the power x. For simplicity, we take the positive power, and then they become n times x, but it is a little bit different from the original definition of E. In the definition of E, 1 plus 1 over n, and it's a reciprocal, but it is not the reciprocal. So I want to replace this one, correct this one by multiplying x in the denominator, but it's a different from original one. Therefore, I multiply x in the numerator too. Then replace this one with n. That's fine because n goes to infinity is equivalent to nx goes to infinity as far as n is a positive. So in this manner, what I have found is just apply the binomial theorem once again. However, in this case, everything else is the same except that I have the same power of the x in the numerator above n to the k, because 1 over n is replaced with 1 over x, the x over n. Okay? Therefore, we can arrive this formula. exponential function can always be expressed as x to the kth power divided by k factorial. Because of very strong constraint that n goes to infinity, whatever value of positive x you bring in, your final result is always convergent to the actual value. So this is a very striking example, exponential function. It can always be expressed in this manner with an arbitrary accuracy. That's a very important. It never diverges to infinity because of the very strong constraint of the coming from the denominator n. By the way, is it also true for a very negative number? Yes, it is true. That one can be obtained by making use of our previous result for the expressing the reciprocal of E. That can be applied to find that in that case what we have found was oscillating factor minus 1 to the k appeared. So either way, we can express the exponential function, whether it's a positive or negative. By the way, this one is identical to this as if I substitute minus x to this x. Therefore, we didn't have to worry about this. So finally, whatever x you may bring in, for example, you bring in x equals 0, the answer is the first term that doesn't have any x. So x to the 0 divided by 0 factorial, that is a 1 divided 1 is 1. So exponential 0 is 1, and whatever real number you may bring in, exponential function can always expressed as an infinite series. This is a very important. Don't forget. And I can extend this one to a complex number. The complex number is, x squared equals minus 1 is the solution of this. For any real number, we square a real number, it is a positive. It can never be a negative number. So we define I to be the square root of minus 1, and we say the solution of this is x equals plus minus I. So, and we remember this magnitude of this, absolute, for example, absolute value. The I's magnitude is 1. A complex number has a magnitude that is, for example, a plus bi. It's a magnitude that is the square root of real part squared and the imaginary part squared. So that's fine. It is a finite number. Why don't we just substitute I multiplied by a real number to the exponential? I don't know how to compute this on the left-hand side, but I know the right-hand side was expressed in terms of this form. In addition, the magnitude of the complex number, pure imaginary number, I, does not grow up to infinity. It is a finite number. Magnitude is 1. Therefore, I claim that the right-hand side is still convergent to a finite number. So let's see what's that. So I can expand this. This k runs from 0 to infinity, and this number can be separated into two pieces. 0 to even numbers, 1, 3, 5, odd numbers. I segregated this odd numbers, and this is even and odd. Okay, and I remember that I squared is minus 1. Okay, so I to the 2n power to k. Okay, that's fine. That is minus 1 to the k. And 2k plus 1. That's minus 1 to the k and I. Okay, therefore I arrive at this formula and substitute. If I substitute, what I obtain is I to the 2k. This is oscillating power. We have also oscillating power, except that 2k plus 1 will give another I. Therefore, I have this form. By the way, did you notice that? This is cosine, and this is a sine. Aha, this is called Euler's formula. E to the I theta is nothing but the cosine theta plus I sine theta. It is a very striking and a very, very useful formula we will repeatedly use in the future. And we say the real part is cosine. Imaginary part, that means the coefficient of a pure imaginary number, I, that is a sine. Very nice. By the way, physicists are brave to apply this power series expansion. Why not to extend to any other very useful computation? In our case, we frequently rotate something, make a transformation using the matrix. Okay, why don't we substitute this? As far as A is a n by n square matrix, number of rows and number of columns are the same, I can always substitute this one to this formula. Okay, so exponential of a matrix, for example, very simple example with the diagonal component. Every element that is not displayed in here, they are all zeros. So diagonal, for example, this is diagonal. 1, 2, 3, 0, 0, 0, 0. This is a diagonal. So diagonal, only the diagonal components are displayed, except that everything else vanishes. In that case, I can make use of the definition of power series expansion. And did you notice that? AB multiplied by AB, the result is trivial. Why? If I multiply this, A squared, and then it's 0, 0, and if I multiply this 0 and this, B squared. Aha! A, B, C, D, E, F, G to the nth power is A to the n, B to the n, C to the n, and so on. Aha! So if I sum them everything all to the infinity, the final result is each element grows up to the exponential of these elements. A very, very interesting thing. But this is this kind of a strange thing happens in physics. Okay, that's it for today. Thank you for listening.